All right, thanks for the preview. Very well done. So the two main topic today is locality. How do we put things that we're going to access, around the same time together so that we don't spend a lot of time seeking. The other is, when the crash actually happens, right? How do we recover it? So the first part is locality. So the simple file system that we looked into last time. So it works. And, as the name suggests, we just want to use a simple one to basically, to capture the concept. So it does this thing, basically supports the basic abstractions like files and the directory hierarchy. It's easy to use, but it's simple, trivial, ends up in a poor performance. So somebody actually did a study, and with the actual user, access pattern and everything, the system was actually delivering only 2% of the overall disk bandwidth, and that's really a horrible performance. So the main reason was that first, it treated the disk like it was, RAM. So the issue here was data was spread all over, right? So it didn't take advantage of the locality. So just to do the positioning and all that, just took too much time and effort. So the system was fragmented as the free space was not carefully managed. So as we've seen previously, so let's say we had allocated A, B, C, D, and let's say the B and D gets deleted. Now the free space is spread out, and let's say the E is actually a large file, then you're spreading all over. So even if you want to actually access the same file, you actually have to do seek of the same file. So that's a problem. The other thing was the block size was actually very small. So it was 512 bytes. So that's also caused a lot of issues. So we come up with something called FFS, which is Fast File System. So also, how do you name things is very important, right? So if you name your system Fast File System, that's like really, really easy to remember, and it represents what it does, right? Any of you want to do a startup, found a company? It's okay. Be ambitious. Anybody want to be a CEO, co-founder? Yeah, cool. Do you have some vague idea of what it will be? Not yet? Have you thought about the name? Although you don't know what it will be. Name is very important, right? So anyways, yes. So with that, so these guys from UC Berkeley permitted Fast File System. So it's actually very simple. I won't say simple, but something that works pretty well. So what it did was it actually kept the same interface, meaning the APIs and all the file system calls that we use is there. We can still use it, but it changed its own internal implementation to be more fast and still widely used, even to these days. So here's a picture of cylinder and all that, but it's not important, but this is just to give you the concept that we want to put things that are related close to each other, and we're going to group some things. So now disk would go into some cylinder groups. Now here you can see a bunch of different plates. Each has, let's say, 4 tracks, right? Now a cylinder, as it says, the tracks at the same distance from center of the drive across different surfaces. So all tracks with the same color, right? So So these are grayscale, so hard to differentiate, but one of the non-black, darkest gray, they're all same color. So these are all the same cylinder. The cylinder group here would be, a set of n consecutive cylinders. So let's say if n is 3, if you start from outside, it will be these 3 except the black one. Now, in reality, modern systems actually organize a drive into block groups, so each of which is a consecutive portion of the disk address space. So by placing 2 files within the same group, FFN ensures that accessing one after the other does not result in long seeks across the disk. So for each cylinder group, we would have something called a super block. So this is for reliability. So basically, in a super block, you can see if this is all correct. The information is, if anything's corrupted. So it actually has some duplicates. So when you're mounting the system, if it looks weird, basically don't use it. You go look for some other super block and just mount that. So for each group, there's an inode bitmap and data bitmap. It basically tracks which blocks of the group are allocated for inodes and data, and of course, inodes and data block. So here, the key policy, as we actually talked about a few times already, is you keep related stuff together. It's common sense, right? This is not rocket science. And also it means keep unrelated stuff far apart. So for example, like when we're accessing files in a directory, a lot of times we access files within the same directory, like when you're coding, right? You could have source code in one directory, you might have binary somewhere else, object first, whatever, right? So a lot of times related stuff should be close together, right? So 2 different ways. First, the directories. So the rule here is you want to find a cylinder group with, number 1, a low number of allocated directories, because you want to balance directories across groups. Okay, you don't want to jam single group with a bunch of different directories. And number 2, a high number of free inodes, because you want to allocate a bunch of files within the directory, right? So these are 2 simple rules, and you put the directory data and inode in that group. So these are rules for the directory, and once you have that, for files, you want to allocate the data blocks of a file in the same group as this inode, thus preventing long syncs between inode and data, right? If your inode and data is actually far away, because you typically first go to inode before you get data. But if even that process involves seeking and all that, that's not very efficient. So you want to place all files that are in the same directory in the same cylinder group of the directory they are in. Again, it's common sense. So example, so let's say we have 10 inodes and 10 data blocks in each group. We have 3 directories. So basically root, /A and /B. And let's say we have 4 files, files C, D, E, and F. Now C, D, E are in the directory A, F are in directory B. Now let's say files are 2 blocks and directories are 1 block. So we have 2 scenarios here. So let's look at the right side first. Let's say we want to load balance, spread things out one at a time, right? We would go here. But if you actually use the policy we just talked about, you could put the root. So first you want to go with the directories, right? So here's the root, directory A and directory B. Now directories are spread out. But then for files, right? So C, D, and E are in the same directory as A. So you put them in the same group. Same with F with B. So if you compare left versus right, when you have to go read, seek, and all that, obviously you know which one is more efficient and fast. So to see whether this is effective, we came up with a metric called the path difference. This basically means how far up the directory tree you have to travel to find the common ancestor of two files. Right? So basically, the more you have to go, right? So yeah, so basically, if you're in the same directory, 0. Right? So here you can see, so let's look at the trace, right? This is the one with, is actually trace with the locality enforced. So even about, like between 5 to 8% path difference 0. Just one is still about 40%, right? So it makes sense to actually take advantage of this. If you do it randomly, then you don't actually see these kind of benefits. Now, so this works pretty well, but we should have one exception, which is the large file. So what we want to do with a large file is, so after some blocks, I allocate it into the first block group. Then FFS placed the next large chunk of the file in another block group. And the next chunk of the file is placed in yet another different group, and so on. So here's an example. So let's say if we don't actually use the exception, ours will basically look like this, right? Now this could be a problem because you might still want to access other files in the same directory. Then you might have to go search a lot of things. So, but for large files, it actually makes sense to spread them out. Now then, obviously the issue could be, hey, what if I'm actually doing a sequential access even for this file? I still have to go look for the next one, which is absolutely true. So then the chunk size does becomes important, right? So if the chunk size is large, the file system will spend most of the time transferring data and just a little time seeking between chunk of the block. So it reduces overhead by doing more work per overhead paid. So deciding on this chunk size is called amortization. Now, if you actually think about it, this transfer rate improves very rapidly, meaning the technology for this is actually improving pretty fast versus the mechanical aspects, right? Like disk arm speed, rate of rotation. So that's pretty slow, right? So you can put that into perspective, and then you can design your system based on that. A few other things about FFS. So internal fragmentation could happen because you have a large block, but there are many files small in size, right? Doesn't make sense. You could actually waste some. So they have a concept called sub-blocks, which is only 512 bytes. So if you create a small file, let's say only 1 KB, it would occupy only 2 sub-blocks instead of having to waste entire 4K byte block. The second one is parameterization. So let's say we have a spindle here. If you do sequential access, a lot of times when you're done with one, right, due to laws of physics, when you're about want to actually access one, this one has actually passed away. So you want to actually spread things out like 0, 1, 2, 3, so that if you do sequential access, you don't actually miss it and actually spin another round. So those kind of things were enable the FFS compared to the older one, and actually also enable longer file names so that we can be more descriptive of the files. The symbolic links were enabled in FFS as well.